Right, so let's get 11.7 done. So just like 11.6, in 11.6 you learned about or probability. So this time we're going to learn about and probability, okay? And probability, just like or, has two different cases depending on what's happening. So or, you are mutually exclusive or not mutually exclusive. As an and, you are either dependent or independent events, okay? So let's talk about the difference between those. So independent events means that the two events that occur, but neither event has an effect on each other. So for instance, like flipping a coin and rolling a die. The flip of the coin has no bearing on what happens if you roll the die. Okay, so if I flip and I get heads on the coin and then I roll the die and I get the number 6, the the heads, because I flipped that, had no bearing on me getting the 6. Or if I flip the coin twice, the first flip has no bearing on the second flip. Okay, so that's what it means to be independent events. The first event does not affect the second event. Okay. Dependent events, that happens when there are two events, and the first one will affect the second one. Okay. So, examples of this, if you are dealing with a deck of cards and I go to my oldest child, Olivia, and I say, draw a card, and she draws one. And then I go to my youngest child and I tell my youngest, Natalia, to draw a card. Natalia didn't have the same opportunity that Olivia had, because Olivia, when she drew a card, there were 52 cards there. When she drew that card, and then I went to Natalia, there were no longer 52 cards left for Natalia. There were 51 cards. Okay. So you can see that the first event of Olivia drawing a card affected the second event because Natalia didn't have the same opportunity. Okay. So dependent events is where the first event affects the second one. So like for instance, when you go, like say you're trying to get tickets to a show, there's like 50 people in front of you and there's only 50 seats. Okay, so that means all 50 of those people are getting that same opportunity, although the ticket count is going down and down and down and down. But when it gets to you, because everybody bought up all those tickets, there are no more left for you. All those events that happened in front of you, where the first person bought a ticket, the second person bought a ticket, and then it finally got to you, number 51, they were sold out because all those events that were in front of you affected your chances of getting a ticket. So again, dependent events. The first event affects the second one. Now, depending on which event you have, if you are independent, what that means you're going to do, so you'll find the probability of each event, whatever happened the first time and whatever happened second, and then you'll find the probability of the second event, and then all you do is just multiply those together. Okay? But it's when it's dependent that you got to be careful, because in dependent events, you will find the first probability like normal, but then the second probability, you've got to find the probability of that event happening, given that event A has already occurred. So like in the example of the cards, where my oldest drew one and then my youngest, when I get to my youngest daughter, she only has 51 cards to choose from then. Okay. So this right here, this notation that you see right here, this is what we call conditional probability. And down below, you see the very mathematical terminology of conditional probability. Again, this is how we find the conditional probability. We take the number of outcomes in common to A and B, and then we're going to put that over the number of outcomes in A. So again, this is very technical, but when we do this with examples, you'll see how conditional probability is really figured. So it's not as hard as what you think that's going on here. I promise you on that. But that's and probability. That's what 11.7 is about. You got to determine whether you got independent or dependent, and then we run our formulas accordingly. Okay? So let's take a look at some examples. So our first example here is not that guy, but it's this one. It says, it is equally probable that a pointer will land on any one of the 6 regions. If the pointer lands on a borderline, spin again, the pointer is spun twice. All right. So down below, I don't know why I typed out red. Fix that real quick. So down below, we want the probability of rolling a green and then a red. Sorry, not rolling, but spinning a green and then a red. And then we want the probability over here that we spin any color other than red, and then we spin another any color other than red. And then the last probability we're going to find is spinning a yellow, then spinning a yellow. But before we can find those probabilities, we have to know, what are we dealing with here? Is this independent or dependent? So does the first spin affect the second spin? So if you answered that as no, the spins do not affect each other, then we are dealing with independent events. Okay, so that means all we got to do is find the probability of the first event, find the probability of the second event, and multiply them together. Okay, going to need to bring up my calculator for this. Let me open that up real quick, because you'll want that to help you with the fractions, because some of these fractions we will have more than one, and we'll want to make sure that we get those reduced answers as well too. So here comes our calculator. Fantastic. All right, so let's go in and let's start finding some information. So the probability of green, then we're going to multiply that by the probability of red. Okay? Well, what is the probability of green? Well, how many green spots are there? There are 2. 1, 2. Out of how many places? 1, 2, 3, 4, 5, 6. So the probability of spinning a green is 2 out of 6. Times, what's the probability of a red? Well, how many reds are there? 1, 2, 3. Again, out of 6. So we're just going to go straight into our calculator and let it do its dancing. Alpha y equals 2 greens. 2 greens out of 6 times alpha y equals 3 reds out of 6 spaces. Hit enter, and there's the probability for spinning a green and then spinning a red, which is equal to 1/6. There we go. So let's do another one. So we want the probability of basically no red, and we're going to multiply that by the probability of no red. Well, how many spaces up here are not red? So if we count that up, we've got 1, 2, 3 out of 6. So the first probability is 3 out of 6. Second probability, because it's not affected, is 3 out of 6. So all we got to do is just multiply these two pieces together. Okay, go to your calculator. Alpha y equals 3 out of 6 times alpha y equals 3 out of, whoops, delete that out. Alpha y equals 3 out of 6. Enter. So we got a fourth as our probability. I promise you, this is how hard ands are. So this is a fourth. There you go. And then last but certainly not least, let's find the yellow. Expand my page a little bit. Okay. So all we have to do, again, because this is independent events, is find the probability of the yellow times the probability of the yellow. Okay. Well, how many yellows are there? There is 1 out of 6. So we're just going to take 1 out of 6 times 1 out of 6, which will give us 1 out of 36. Done. See, and's not that hard. So here we're using that same spinner, but this time it's spun 3 times. So go ahead and pause the video. You already know that this is going to be independent, because if it's independent with 2 spins, it's not going to change anything if you do it a third time. So go ahead, pause the video, find these 2 probabilities, and go. Okay. So, going to come back into my page. So we want the probability of a green, and since this is independent, we just got to find that, times the probability of a red, because the second spin isn't affected by the first, times the probability of a yellow. Okay, because it's all independent. The first spin doesn't affect the second, doesn't affect the third. So the probability of a green, as we already knew, was 2 out of 6. Probability of a red is 3 out of 6. Probability of a yellow is 1 out of 6. Again, you could reduce these fractions and then multiply it all out. That's A-okay, but you don't have to. So just so you know, I'm not always going to go back to that calculator screen that you saw, because you all have your calculator. You know how to input fractions. So you just go into your calculator, input those fractions, and let the big dog eat. So if we take 2 6 times 3 6 times 1 6, we get 1/36 as an answer. See, not that hard. So down below, we want a red every time. So all we're doing is taking the probability of a red times the probability of a red times the probability of a red. Well, the probability of red is 3 out of 6 every time. So we go to our calculator, and all we got to do is put in 3 out of 6 each time. So 3 out of 6 times 3 out of 6 times 3 out of 6, and that gives us 1/8. There you go. Again, that's all it takes to do independent and probabilities. So here we got a single die is rolled twice. So I want you to think about this. Is this independent or dependent? Go ahead and pause the video. Give this one a shot. Okay, so hopefully when you thought about this, that this is independent, because the first roll is not going to affect the second roll. Okay, so this is definitely all independent. Still working with that. So you could have done these probabilities real quick, because all we need is the probability of rolling a 2 times the probability of rolling a 3. And if you don't remember, the outcomes for rolling a die are 1, 2, 3, 4, 5, 6. So what is the probability of rolling a 2? Well, there's only one way to roll a 2 out of 6. Times the probability of rolling a 3. There's only one way to roll a 3 out of 6. So I'll give you 1 out of 36. And there you go. Down below, again, these are all independent, so we need a probability of an even times the probability of a number greater than 2. Well, how many evens are there? There's 2, 4, and 6, so that's 3 out of 6. How many numbers are greater than 2? Well, there's 3, 4, 5, 6, so that's 4 out of 6. So this will give you an answer of alpha y equals 3 out of 6 times alpha y equals 4 out of 6, 1/3. There you go. Again, when it's independent, all you got to do is find the probability of the first event, multiply it by the probability of the second event, and so on and so forth. All right, so this time you draw one card from a 52 card deck. Then the card is replaced in the deck is shuffled, and you draw again. So on this one, I've got 3 of these. Go ahead, pause the video, think about if this is independent or dependent, and then find me the probabilities, and go. Okay, so hopefully you said that this is independent. Reason being is because we are going to take and we're going to put that card right back into the deck. We are replacing it. Anytime you replace something, you're right back to the beginning. So that's why this is independent, because the first time you draw, you got 52 cards. When you put that card back, there are still 52 cards there. So it's the same deck that you had the first time you went around. All right. So since this is independent, all we need to do, stuff's moving around on me. Let's unhighlight that. So we need to find the probability of a picture times the probability of a heart. Okay. Let's go into page width. Well, how many picture cards are there? There are 12 out of 52. How many heart cards are there? There are 13 out of 52. So all we need to do is hit alpha y equals and put in 12 out of 52 times alpha y equals 13 out of 52. And we get 3 out of 52 as our probability. See, not that hard. You just have to remember about a deck of cards, though. So the next one, we want a probability of a king each time. So probability of a king times the probability of a king because it's independent. Well, how many kings are there? There are 4 out of 52. Times how many kings are there again? 4 out of 52. So what does that give us? Well, alpha y equals, we're going to have 4 out of 52 times alpha y equals 4 out of 52, 1 out of 169. Okay? So then the next one, a black card. Okay? Well, that means we want the probability of a black card. Usually I abbreviate it just BL. And then we want the probability of a black card. Well, how many black cards are there? There are 26 black cards out of 52 times 26 out of 52. And that will give us an answer of 1/4 when all is said and done. Again, when they're independent, all you do is you find the probability of the first event times the probability of the second event, or third, so on and so forth. All right, so this guy right here, it says the probability that South Florida will be hit by a major hurricane, category 4 or 5, in any single year is 1/16. So down below, we want to find the following 4 probabilities. All right. And that is factual. Again, the source comes from the National Hurricane Center. So this is true facts. So that is the probability that South Florida could be hit by a hurricane 1/16. So let's come in. Let's look at A. So A says, what is the probability that South Florida will be hit by a major hurricane 2 years in a row? So we want the probability of 2 hurricanes. Now, because we get hit by a hurricane 1 year, does that affect us being hit by a hurricane the following year? No, it doesn't. Okay, just because we get hit 1 year doesn't mean that the next year it will bypass us completely. Hurricanes don't go, oh yeah, we hit that one last year, so let's give them a break. Hurricanes don't have that kind of discussion. Okay, so when you're looking at this is an independent type of situation. Because just because we get hit by a hurricane 1 year doesn't mean that next year we won't get hit again. So since these are independent, all we have to do is find the probability of a hurricane hitting 1 year and multiply that by the probability of a hurricane hitting the next year. Okay? So what's the probability of getting hit by a hurricane 1 year? 1/16. And what you hear, if you hear it, is my wife's phone going crazy. So 1/16 times 1/16 is going to give us the following probability. Alpha y equals, and I do want to put this on the calculator. I do want to show this one. So alpha y equals 1/16 times alpha y equals, second quit. Scrolling all the way over. Alpha y equals 1/16. And there is our probability, 1 out of 256. Okay? And that is part A. Part B says, what's the probability that South Florida will be hit by a major hurricane 3 years in a row? Okay. So it's a lot like what we just did in Part A. So probability this time of 3 hurricanes. So basically all we're going to do is take what we just did in Part A and tack on another 1/16. So it's the probability of a hurricane times the probability of a hurricane times the probability of a hurricane, which is 1/16 times 1/16 times 1/16, which when we multiply all that out, show you on the calculator, a nice quick way to do that. You can just scroll up, grab the 1/16 you multiplied, and all we want to do is just do another one. Look how fast that is. Put in our next piece of 1/16 and hit enter. So 1 over 4,096. And there you go. That is the probability of getting hit by a hurricane 3 years straight. Okay. Now, part B says, what is the probability that South Florida will not be hit by a major hurricane? So this is going back into 11.6. And 11.6, remember I talked about probability of something not happening. And the probability of a hurricane not happening, that's equal to 1 minus the probability of a hurricane actually happening. Okay, so you want the probability of something not happening. All you have to do is take 1 minus the probability of it actually happening. So in our case, all we have to do is take 1 minus the probability of a hurricane happening, which is 1/16. And 1 minus that is 15 over 16. So that is the probability of a hurricane not happening. But what C wants to know about is what's the probability that there will not be a major hurricane for the next 10 years. So I want you to notice something. I mean, we can actually write this out. If you want the probability of 10 non-hurricane seasons, you can come in here and you can take the probability of a not hurricane times the probability of a not hurricane times all the way out to multiplying by the probability of a not hurricane. And you'd have that 15 over 16 10 times. Oops, I don't know why I put 2 there. Should be a 10. Again, you can go to the calculator, you can do it this way, but I'm going to show you a faster way to do this. There's another way that we could have put the 1/16 into the calculator times the 1/16. Because these are the same, that just means it's like exponentials. We're taking 1/16 and we're squaring it. The same thing for B. We're going to take the 1/16 that we had here, and since we're multiplying it 3 times, it's just like cubing it. Okay? And then, so down here, we're really taking 15 out of 16 times 15 out of 16 times 15 out of 16 10 times. So another way to think about this, easier way to put it in the calculator than typing all that out, is just go in and put 15 over 16 to the 10th. And this is going to kick out a decimal answer, and I want to go ahead and round to the nearest thousandth, which is 3 decimal places. Now, I don't remember what the book makes you round to, but I'm just letting you know what I want to round to. So, parenthesis, alpha y equals 15 over 16. And we're going to raise that to the 10th power because we want it for the next 10 years. And there is our probability, 0.52. And that second 4 says, hey, first 4, stay the way you are. So rounding to the nearest hundredth, 0.524. And that is the answer to part C. Okay? Part D says, what's the probability that South Florida will be hit by a major hurricane at least once in the next 10 years? All right. So probability that we are being hit by at least one hurricane for the next 10 years. Well, let me show you something. Right over here is a formula for dealing with at least once. The probability of an event happening at least once, all you're going to do in order to find that probability of at least once, you're going to take 1 minus the probability that the event does not happen. Okay? Taking 1 minus the probability of the event that does not happen, that is the same thing as at least once happening. Oh, wait a minute. So if I want the probability of at least one hurricane over the next 10 years, so this is D that we're working on here, we're taking 1 minus the probability of no hurricane over the next 10 years. Don't we have this probability somewhere? Oh, there it is. All we have to do is take 1 minus that number. So I'm going to go into my calculator because I want to keep this as accurate as possible. I'm going to take, instead of using that rounded number, I'm going to come right back up here to this number we just found, and I'm going to use it down there. So all we have to do is take 1 minus this number right there, and then let's round to the nearest thousandth. So we get 0.47. This second 5 says, hey, first 5, go up. So 0.476. There's the answer to part D. Not too crazy. I think this is as hard as what these problems get in your assignment, so definitely pay attention to this one. That's why I did this one together with you guys. So be careful. All right, not a lot left, okay? So I think I got 3 more examples, then I have a survey example, and that's the last one right there. All right. So in this example, it says I have a box of chocolates for the class. There are 30 chocolates in the box, all identically shaped. 5 are filled with coconut, 10 with caramel, and 15 are solid chocolate. You randomly select one piece, eat it, and then select the second piece. So real quick, think about whether this is independent or dependent. So if I have a box of chocolates and I came up to you guys in class and I gave you the box and you selected one, then you ate it, and then selected another one because you're greedy like that, do you have the same opportunities as you had the first time you chose a chocolate to the second time? So did the first time you grabbed a chocolate and ate it, are you now affected by that the second time? And think about it. All right, so if you said yes, you are affected, then that means this is dependent. Okay, and it is a dependent event because once you eat that chocolate, I'm not asking you to regurgitate it back up into the box. That's just gross. Okay, we don't do that. All right, so these are dependent events. So this is where we're going to start talking about that conditional probability. So for this guy, what we want to do is SC stands for solid chocolate. Okay, CO stands for coconut. CA stands for caramel, and it is caramel. Okay, so probability of solid chocolate is what we want first. And then we've got to find the probability of a solid chocolate again, given that we just ate a solid chocolate. Okay, so let's find this first probability. How many solid chocolates are there in the box? And there are 15. Out of how many total? 30. So 15 out of 30 times, all right, so we just ate that solid chocolate. So there aren't 15 anymore. There are 14. And because we ate one, there aren't 30 chocolates in there. There are 29. You see how everything is affected now? It's not the same box anymore. So now when we go back and we want to do another solid chocolate, well, how many solid chocolates are left? 14. Out of how many chocolates total? 29. So this is what we're going to go to our calculator and run the multiplication of the fractions on. So 15 over 30 times alpha y equals 14 over 29. And there is our probability, 7 out of 29. So let's go up here, do some quick erasing, and let's do this again. Okay? So that was solid chocolate. So this time, again, this is a dependent event. So we're going to find the probability of coconut times the probability of a caramel, given that we just ate coconut. Okay? So let's find this first probability. How many coconut are there? There are 5 out of 30. Okay. But again, we just ate one of them. So there are no longer 5 coconut. There are 4. There are no longer 30 chocolates. There are 29. So we scroll back down. Now we want a caramel. We want the probability of a caramel. Okay, so we go up here. How many caramels are there? There are 10. Out of how many chocolates? 29. Okay, easy peasy. So that's what we have to multiply. So alpha y equals, using my calculator because you guys know how to run this now, 30 times alpha y equals 10 over 29. And we get 5 out of 87. And there you go. And that's how conditional probability is dealt with. You just got to look at what's going on, okay, with your situation. So that big technical mumbo jumbo math formula that I showed you, I mean, that's the technical math way, but you don't have to really think about that. You can think about it in terms of, what's really going on. Take out what's been done, okay? So I've got 2 more here. Take a look at these 2. Pause the video here in just a second. Again, think about whether these are independent or dependent, and then find their probabilities. And go. Okay, so let's take this out of dual screen. Hopefully you notice that both of these were dependent events. So in this one it says, a political discussion group consists of 5 Democrats, 6 Republicans, and 4 independents. Suppose 2 group members are randomly selected in succession to attend a political convention. So in succession means that I'm going to pick someone, and then I'm going to grab another someone. I'm not grabbing them both at the same time. I'm grabbing them one after another. Okay? So the moment I grab someone from this group, the group has now dwindled in size. So the next choice I have is now affected because I've already pulled someone out. That's why, I wrote independent. That's why this is dependent. Because when I go to select my next person, I don't have the same size group or the same number of people representative in each group anymore, just like the chocolates. So here, we want to find the probability that the first person I select is a Democrat, and then we're going to find the probability that the second person I select is a Democrat, given that I've already pulled the Democrat. Okay? Well, what is the first piece? Well, how many Democrats are there? There are 5 in this group. Out of how many total? Well, if you take 5 plus 6 plus 4, it gives you 15. Well, so there is no longer a total of 15 because I just pulled one person out. That's going to give me 14. There are no longer 5 Democrats. There are 4. So when we do this next piece, how many Democrats do I have left? 4 out of how many? 14. I about wrote 15. Silly me, because there are only 14 people left. And then that will tell me my probability. So we just go to our calculator and alpha y equals all this good stuff. Let the calculator do its job. And you will end up with 2 out of 21. There's your probability. Okay? And now we're just going to repeat the experiment again with choosing an independent first and then a Democrat. So we're going to need the probability of an independent. And we're going to multiply that by the probability of an independent, a dependent, not dependents, Democrat, given that we've already taken out the independent. Okay? So what is the probability of an independent? Well, how many independents are there? There are 4 out of 15 times, okay, well, we come up here, fix this. There are now 3 independents left. There are a total of 14 people left. So we want a Democrat. How many Democrats are there? There are 5 left out of 14. And if you notice, these are the same fractions that we had just a second ago. So you'll end up with 2 out of 21 again. Okay? Pretty much the same fractions because you're going to take 4 times 5, 4 times 5, 15 times 14, 15 times 14. It's the same. Okay? There we go. One last example before our final one. So in this one, it says you got an ice chest that contains 6 cans of apple juice, 8 cans of grape juice, 4 cans of orange juice, and 2 cans of mango juice. Suppose that you reach in to the container and randomly select 3 cans in succession. So you reach in, grab one, pull it out, reach in, grab one, pull it out, reach in, grab one, pull it out. That's what's going on. So we want the probability that this is going to pull out 3 apples. And again, this is dependent because the moment I pull out a can, it's not the same ice chest anymore. Okay? So we want to find the probability of an apple and then multiply that by the probability of an apple, given that I've already taken 1 apple out, times the probability of another apple, given that I've taken the 2 apples out before it. Okay? So what's the probability of 1 apple? Well, there are 6. Out of how many cans are there? Add it all up. 6 plus 8 plus 4 plus 2 is 20. Times, well, okay, so the 6 is now a 5, and there was a total of 20, which that 20 has now turned into 19 because we took a can out. So how many apples do I have now? I've got 5 out of how many cans? 19. So now we're going to mess with that. That 19 now becomes 18. The 5 becomes a 4. So now the probability we have is 4 out of 18 for that last can. So we go straight into our calculator and just take 3 fractions times each other this time and let that calculator again do that hard work, okay? So alpha y equals, put in the 6 over 20, scroll out to the side, times alpha y equals 5 over 19, times alpha y equals 4 over 18, and we've got a 1 in 57 probability for that. Okay? And now we're just going to repeat it for apple, orange, and then mango. Okay, well, that's not too hard. So come up here, do some quick erasing. We'll put the 20 back there. All right. Come up here, erase that guy real quick. All right. So we need, on this one, the probability of an apple. And we're going to multiply that by the probability of an orange, given that we took an apple. And we're going to multiply that by the probability of a mango, given that we took an apple and an orange already. Okay? So what's the probability of an apple? Well, we already know that, 6 out of 20. times, okay? So this 6 is now 5. The 20 is now 19. Well, how many oranges are there now? Well, there are 4 cans of oranges, okay? So that will be 4 out of 19 times, okay, let's do some adjusting again, just like what we did. So we took one of these guys, so there are 3 oranges now. We took out a can, so there are 18 total cans left. So now we want one of the mangoes. So there are 2 mangoes out of 18 now. So all we do now is go back into our calculator. I can select those 3 fractions I just had. All I got to do is go up and change those top values to a 4, and then the last one to a 2. And I end up with a probability of 2 out of 285. And last but not least, what if we want the probability of no grape? Every time we pull no grape. Okay, so it doesn't matter what cans we grab as long as it's not a grape. Okay, so if we're looking at this and thinking about their probabilities, there are a total of 2, 6, and 4, 12 cans that are not grape. So when we deal with this guy, we're going to find the probability of no grape, which is 12 out of 20 times. We want, again, another probability of no grape, given that we already took out a no grape. So if there were no grapes, there were 12 to begin with, and the total was 20. So we took out a no grape with 11. Total is now 19. So there's your next probability. 11 out of 19 times, and our last probability, we want the probability of no grape, given that we took a no grape and a no grape. So again, we took out a no grape, so there are 10 left out of 18. There's your last probability. Okay, fix my 10 so it doesn't look so much like an 8. So we just go straight to our calculator. I'm going to grab my fractions that I just had a moment ago and just adjust my numerators. So 12 out of 20 times 11 out of 20, or out of 19, times 10 out of 18. And the probability is 11 out of 57. And there we go. So as with anything in our section, since this is our last one in chapter for chapter 11, they put it kind of all together. So in here, you got ands, you've got ors, you've got regular probabilities. So go ahead and pause the video, give this a shot. Remember, when it comes to ors, you got to know whether they are mutually exclusive or not. And when it comes to ands, are they independent or not? And go. Okay, so up here, when we're looking at this first probability here, oh, not dual pages. We don't want that. I want page width. So the first one just says, what's the probability of selecting someone that's not widowed? Okay. So, well, how many people are not widowed? Well, that's all 3 of these numbers that are right here. These are the people that are not widowed. Again, we don't care whether they're female or male. We just want not widowed. So if we take 133 plus 81 plus 26, we get 240. Out of, well, how many people did we talk to? 254. So this one was just that regular probability that we learned about back in 11.4. Okay? So we go to our calculator, alpha y equals, let the big dog eat, 240 out of 254, and we get the probability of 120 out of 127. There's your probability. So that was just going back all the way from 11.4. Right here, these two are definitely from 11.6. So in this case, to be widowed or divorced, is that mutually exclusive or not mutually exclusive? And in this case, these are mutually exclusive. You cannot be both at the same time. Let me explain why. I am a person that has been married. I am on my second wife, but I have been married before, so I was divorced. So when I go and fill out an application, it doesn't say select all that applies. When they ask you if you're single, married, divorced, whatever, it says select one. You select your most current situation. So even though I have been divorced before, I am now married. So I will always select married. Okay. So that's why this is mutually exclusive. You're not going to be both. You're going to be, what is your current situation? Either you're a widow or you're divorced. Okay. You're not both. So since this is mutually exclusive, all we're going to do is find the probability of being a widow and add that with the probability of being divorced. Okay. So let's go up. Let's find the probability of being a widow. How many people are a widow? Well, that's right here, 14. Out of how many total? 254. Okay, so there's my first probability. 14, 254. Okay. Next one says, well, what's the probability of being divorced? Well, how many people are divorced? 26. Out of how many? 254. That was 26. And again, you can just let your calculator do the work for you. Okay, go into your calculator. Alpha y equals 14 over 254. And then we're adding alpha y equals of 26 over 254. And it reduces to 20 over 127. And there you go. Okay. Now the next one, if you think about this, are these two mutually exclusive, being female or being divorced? And these are not mutually exclusive. You can be female and divorced at the same time. Okay? So, with that being said, when we run this OR situation, we need to find the probability of being female, add that with the probability of being divorced. But because we're counting everybody twice here, because they have stuff in common, you can be female and divorced. I don't know why I put an equal sign. I need to subtract out the probability of both female divorced people. So when we come up here, let's do this real quick. How many females do I have? Well, I have 131. Out of how many total? 254. So 131 out of 254. Okay. Plus, well, how many people are divorced? Well, that's 26 out of the 254 again. But I have to take out all those people that have been female and divorced in that category because we just counted them all twice. So how many people are female and divorced? That are both? That's the 15. Out of how many people total? The 254. So there we're taking out all the people that we counted twice. And so we just go to our calculator, let it do its job. I'm going to go back up and grab those two fractions I just worked with, because all I got to do is change that first fraction's numerator. And then all I got to do is add in one more fraction where we're going to subtract off the 15 over the 254. And that gives you 71 out of 127. Okay? Two more problems, and then that wraps up 11.7. So down here, these ones are truly conditional probabilities. So what is going on in this is we're going to tell you that right here, I want the person to be divorced. I only want you working on the people that are divorced, okay? So when we come up here, that means we're only going to work in this category right here, okay? We are only working in the divorce category. That's what this part right here that says, given that the person is divorced. You're only working with that. So in order to find this probability, we need to figure out, well, how many males are there in that category out of the total? Well, how many males are there? 11. Out of how many total? 26. There's your probability. So that's how this piece worked. Okay, this told you what column to focus in on, and then you just find your probability within that column. They wanted men out of the total. Okay, the last one works the same way as that. If you want to pause the video right now and give it a shot, go right ahead. So we want the probability of being widowed, but you have to be female to begin with. Okay. So go ahead and pause the video if you want. Again, you want to be the probability of being widowed, given that you are a female to begin with. So if I come up here, pause the video, and go. All right, so you have to be a female. So we're focusing in right here only. Okay, so we want the probability that you are a widow. Well, how many widows are there? 11. Out of how many females total? 131. That's your probability. Okay, 11 out of 131. And you should always check to make sure that these things reduce. Okay, but the past two probabilities did not reduce. And that, my friends, is 11.7. So we have completed chapter 11. Please make sure that you do all assignments and do not forget about chapter 11 review and the chapter 11 review quiz. Good luck and have fun.